All right. I think this is going to get a little bit scary, but again, by doing the reading in the book and by working our way through this lecture and so on, I think you're going to be ready for any questions that come up about this. Remember, what we're trying to figure out is what will a wind profile look like near a shoreline or any other situation where there is a boundary between two different regimes of the surface parameters, like the aerodynamic roughness length being very different over the lake than over the city, or the friction velocity, or it could also work, by the way, for other parameters like the heat flux and so on. Alright, so we've got some kind of transition zone there. We gotta wonder what the wind profile, if we could like have a wind profiler at that location that I have circled there with yellow and red, what would it even look like? Now, I'm going to tell you it's going to be a whole lot easier to figure this out and to visualize it if we switch from our fairly simple kind of view of a wind profile to the one that's plotted on Semilog graph paper like this. Because remember, the log wind profiles are just straight lines when our y-axis is logarithmic. I know not everybody loves Semilog paper and all that kind of good stuff, but this is a good example of the kind of problem that's a whole lot easier to solve if we think about it this way. So once again, we still have two wind profiles here, but they look like a straight line when we use that log paper. Again, the blue curve there is for over the water, and the green curve is over the city. You happen to use forest parameters, but they're not all that different from urban parameters there. Now, what will the wind profile at that location that goes through that transition zone look like? It looks like this charming equation here. Oh, no, don't go and don't go over to log into the registrar's website and drop the class. No. I know this is horrible. This looks like an equation that would describe something horrible, like the destruction of a city by aliens.
So, this all seems horrible.
Okay, so that was just a little gag from the Avengers. You might remember that movie. And I gotta say, this equation does look horrible. Bruce Banner is right on that point. But, maybe this isn't so bad. I mean, maybe we don't need to be afraid and think we gotta drop a class over a scary-looking equation. We're big kids now. We can figure this thing out. Well, the first thing I see here is that there's actually like three equations here that we apply under three different situations. We don't yet know what all these symbols mean, but clearly if the z, the height, is greater than or equal to something, we apply the top equation. If z is less than or equal to something, we're going to be applying that bottom equation. And if z is between those two things, we're going to apply the middle equation. Okay, I like that. Nobody likes that kind of notation, but it works. I see what we're doing here. We have three different equations here. Now, if you actually read the book, you'll see that C1 and C2 are just two constants that are defined in a journal article, and that there's some bickering in the scientific literature about precise values to use, but good consensus values to use happen to be 0.3 and 0.09. Okay, so we can just, they're constants. Life's short. They're constants. What is this h? Because, I mean, we always use the C1 with an h, and we always use the C2 with an h. H is going to be the symbol that we're going to use for the height of the top of the internal boundary layer, or IBL. Now, we have not yet said what an internal boundary layer is. We're going to come back and talk about that in a little bit, but it's going to be part of our boundary layer. And it's going to extend from the surface to some height, and that height will be h. So, C1 is 0.3 times h, or 30% as high as the top of the internal boundary layer, and C2 is 0.09 times that height, or 9% of the height of the top of the internal boundary layer. So all of these numbers, C1h and C2h that you see all over the place in here, are just describing three places in the vertical column. H is the top of the internal boundary layer. It's going to be part of the boundary layer. It's going to be as much as maybe a few hundred meters or something. And there's two heights along the way. 9% as high as that, and 30% as high as that. Okay, horrible to look at, but actually not that terrible once you think about what they mean. Effectively, we have now divided this equation up into three regimes where we're going to be applying the three different forms of the equation right here. The purple one at the top is the one we're going to use for heights greater than 30% of h. In other words, the top 70% of the internal boundary layer gets that equation that's in the purple box. The bottom equation, the one I've boxed in there in blue, is the one that we're going to use below for heights less than C2 times H, the lowest 9% of the internal boundary layer. That's going to be that blue box. And that red one is the equation that we're going to use for heights between the 9% of the internal boundary layer and 30% of the internal boundary layer. So the middle 21% of the internal boundary layer gets that equation. Okay? I don't like that notation. You don't like that notation. It all looks horrible. But okay, I get it. It doesn't seem so awful. I mean, maybe it's not so bad. I could picture that on my graph here. Again, thinking about this on this Semilog paper here, we're going to have some height h. That is the top of the internal boundary layer. Remember, it's a part of the boundary layer. And I hate the fact that it has name so close to boundary layer. But, okay. Like in this case, I just drew h at 100 meters. 100 meters is a perfectly reasonable height for the height of the top of the internal boundary layer. And I just put a solid line there. Then C1H is 30% of that, and C2H is 9%. Gosh, it doesn't look right until you remember that that's a log scale over there. Okay? C2H is at 9% of 100, so it's at a height of like 9 meters. And C1H is at a height of 30% of H, or about 30 meters, just it's log paper, so it's kind of a mess to see how the scale works. Okay, so, but I mean, okay, once I've got it on there, I could picture, I'm going to be applying each of those equations to each of those three little parts, those three little layers I've just sectioned off there of the profile. All right, let's look at the top one. U star 1 over kappa log z over z naught 1. Hey, that's just the log wind profile. That's the log wind profile from the upwind conditions where U star was U star 1, whatever the value of U star was over, in this case, the lake. And Z naught 1 is just the value of the aerodynamic roughness length over the lake. All that is, that top purple equation, is the piece of the log wind profile from over the lake, but just the part in the top 70% of the profile. Okay, so I've highlighted that with red. That is a piece of our wind profile. Above C1H, the top from 30% of the height of the internal boundary layer on up, that is the wind profile. It looks exactly like the wind profile over the lake because that's air that doesn't even know we're not over the lake yet. It hasn't mixed with any air from the surface. It hasn't, okay. That makes sense. That's flow that doesn't yet know that there is a different surface there. It hasn't yet experienced that those air parcels haven't touched the surface, they haven't mixed with air parcels that are from the surface. Okay, that's the top part. All right, let's look at that bottom part there. U star 2 over kappa log of z over z naught 2. Hey, that's just the log wind profile equation. And it's the log wind profile for the downwind conditions, namely like over the land or whatever, where U star 2 and Z naught 2 are the appropriate values for over the land. And that is done for the heights that are below the lowest 9% of the internal boundary layer. So I've actually just marked those in red there. That's just the same, that's literally just that land profile, but from 9% of the atmosphere, not 9% of the atmosphere, 9% of the internal boundary layer down. Okay. Again, that kind of makes sense. That's the surface that is already, that's the part of the atmosphere that has already completely adjusted to this new surface regime. That is air that has already experienced the new friction profile and now can, has responded to that. Fantastic. So two parts of our wind profile here are actually pretty straightforward. Now, what are we going to do about in between here? That part that's labeled in red is horrible, right? I mean, that doesn't even look like anything good at all. And part of the problem with this is the notation. Now, your author has kind of, then make sure you read those paragraphs there, but he's explained that U double prime, that is actually the wind speed at the top of that bottom layer. Does that make sense? Like at 9% of the height of the internal boundary layer. So that is U double prime. And U single prime is the wind speed at the bottom of the top part of the layer. Again, it's the wind speed, I gotta have it graphically analyzed there, but it is just the wind speed, that we read off of there. We'd have to plug in the height and so on. It could be done though, and your book actually gives you the equations. I'm trying to simplify this a little bit here. So the U double prime and the U prime are not really all that big of a deal they're just numbers you plug in from the log wind profile. Okay, that doesn't look so horrible. The rest of this, though, might look familiar depending on what classes you've had in physics or atmospheric science or something like that. That's just interpolation. That's just kind of blending a value from the top to the bottom of like a layer. Now in this case it's actually done in semilog coordinates and so on. But this is actually not so horrible. It's just interpolation. All we're doing basically is just smoothly transitioning from the value at U double prime to the value at U prime. In other words, look what I did with that red line there. Effectively, we're just connecting the dots, admittedly in this semi-log coordinate system and so on. The math is not trivial, but the idea is basically we've just connected the dots here. We've created a smooth transition through the transition zone, where the wind speed is adjusting from at the bottom of that transition zone, being consistent with at the land, to at the top of that transition zone, being consistent with the value for the upwind surface, in this case the lake. That's all it is. Okay, that is ugly math for what's really not that complicated of an idea. Graphically, we could do this fairly straightforward, in a fairly straightforward way. Actually, mathematically modeling this on a spreadsheet is not so simple. Now, in this particular case, I wanted to draw your attention to the fact that, keep in mind, the slope of this line is about wind shear. Remember, wind shear is change in wind speed with respect to height, or du/dz. I hate that. It's partial u, partial z, but whatever. So the slope of that line tells us something about wind shear. In this case, you can see how we have some wind shear below the transition zone, and we have some wind shear above the transition zone. But in this case, look at all that wind shear we've got going on in the transition zone, where the slope of this line is pretty, every meter we're going up, we're creating a lot of wind shear. The wind speed is increasing. So in this case, it wouldn't have to be that way, okay? It just, in this case, there's a lot of wind shear on this boundary, which makes it has interesting applications in like aviation operations and so on. All right. Notice that all of this depended on that value of h. The height of whatever the heck an internal boundary layer is, the height of it determines this whole structure here. So like if we were at a place where the internal boundary layer's height was lower, well then 9% of that is closer to the ground, and 30% of that is closer to the ground, and the whole structure of this becomes less thick, which is, what we saw closer to the shoreline in that yellow and red circle there. In the same way, if we were at a location where the height of the internal boundary layer's top was higher, well then we kind of stretch the whole thing out and these layers become thicker. 9% of the height of the top of the internal boundary layer is higher, and 30% of the height of the top of the boundary layer, internal boundary layer, is higher, and we kind of stretch the whole thing out the way it is like farther from the shoreline here. Okay, I'm starting to be able to picture this here. Okay. Now all through this presentation I've been drawing this transition zone, like the top and the bottom of it were parallel, because that was a simpler thing, but notice the teaching technique here. Now I'm going to refine this idea. Alright, this isn't quite right. The top and the bottom of the transition zone aren't parallel to each other. You gotta think about how they're related to h. The bottom and the top of the transition zone are at 9% of the height of the top of the internal boundary layer, and 30% of the height of the top of the internal boundary layer, respectively. So that transition zone is actually kind of wedge-shaped. The value of h, that internal boundary layer's height, starts at 0 at the coastline, and it increases with respect to height as you get away from the coastline, or the boundary between two different surface regimes. And so as we get farther and farther away from that coastline or whatever, H is getting higher and higher, which means at first, the bottom and the top of the transition zone are kind of pinched to 0. But as we get farther and farther away from the coastline or whatever this boundary between the two surface regimes are, the bottom of that layer gets higher and higher above the ground, the top of the layer gets higher and higher above the ground, but the layer itself, the transition zone itself, is getting thicker and thicker, as in, the distance between the top and the bottom of it are getting farther and farther apart. They still, though, constitute 21%. The transition zone continues to constitute 21% of the depth of the internal boundary layer. Cool! So, how high above the ground is this value of H, this internal boundary layer height? Well, now, that gets to be a bit messy. I mean, some distance away from the boundary, so like some distance X meters from that boundary between two different surface regimes, like the shoreline or whatever, you can figure out a value for H. But as the book shows you, it's messy. It's not perfect, it's just an estimate. It can't be solved analytically, like you can't just plug numbers in and you get the number out. It has to be solved numerically. It can't be solved, the right word for that is analytically. Let's not go there, okay? The basic idea, though, is there's sort of a slope to that H, that internal boundary layer. And a way to kind of think about it is the bottom of that transition layer is going to be sloping at a rate approximately 1 to 100. In other words, for every 100 meters you go in, the bottom of that transition layer will be up about 1 meter. Which means, since that's only 9% of the height of the total internal boundary layer, that means for every 100 meters you go in from the shore, the top of your internal boundary layer has raised about 10 meters or something like that. But that's just sort of ballpark, giving you a sense of the slope of these features here. Now, it's time to answer a hard question. And these have all been hard. But if this H is supposedly the top of the internal boundary layer, don't you think we ought to know what that is? What is an internal boundary layer? And you're not going to be happy with what I've got to tell you here. Here, I won't be the bringer of bad news. I'll let the Glossary of Meteorology do it. The Glossary of Meteorology is a big, thick book published by the American Meteorological Society. And it says the internal boundary layer is a layer within the atmosphere bounded below by the surface and above by a more or less sharp discontinuity in some property, like turbulence or something like that. So the internal boundary layer has to have the bottom of the atmosphere, the surface of the Earth as its bottom, and then it separates with something very different above and something very different below. Internal boundary layers are associated with horizontal advection of air across a discontinuity. Advection, horizontal transport of air. Advection means like transport of air across a discontinuity, like a shoreline, or the boundary between, an irrigated surface and a dry surface, or something like that, in which a property like the aerodynamic roughness length or heat flux or something that can be viewed as layers in which the atmosphere is adjusting to its new surface properties. Internal boundary layers are part of the boundary layer. They really needed a better name for this. It's a part of the boundary layer. The boundary layer extends, 1 to 2 kilometers up. The internal boundary layer is, that layer nearer the surface where things are adjusting to a change that just happened. As the air flowed from one surface to another and there's a change, the change is happening, the adjustments are happening inside of the internal boundary layer. And here's just a good example of that. Here is flow coming from the land toward a lake, and then as the air reaches the lake and changes from one surface to another, there's a very different roughness length, there's a very different evaporation rate, there's a very different heat flux, and so on, and you can see the atmosphere is adjusting. Now in this case, part of how it's adjusting is that it's starting to develop fog. So in this case, as we get a few meters from the shoreline, you can see that there's an internal boundary layer bounded by the surface and some height above the ground. In this case, it looks like it's only a couple meters, in which the atmosphere is adjusting to these new surface parameters. In this case, it is having evaporation and heat fluxes and so on that are resulting in the formation of fog. But it's just a layer of the atmosphere near the surface where that adjustment is happening. This is actually, again, not the whole boundary layer. It's just a piece of the boundary layer where this is happening. This business of internal boundary layers is actually very challenging in atmospheric sciences. It's active research to figure out how to simulate this, how to quantify this, and so on. But the idea that where a change is happening at the surface, you're going to have this growing layer as the flow goes from the upstream to the down, from the upwind to the downwind side, and the adjustments are happening in this case to the wind profile, but it could be something else. It could be moisture profiles or whatever. That's going to be important in the context of wind energy, because if your wind turbine is near some kind of boundary, we're going to need to know, will it be above or below the transition limit? Will it have a wind profile more characteristic of the downwind side? Will it have a wind profile more characteristic of the upwind side? Is that advantageous to you in terms of the amount of power you're producing and so on? All of, would it be better to make the tower a little taller? Is there no economic benefit to making the tower a little bit taller because you aren't increasing in the wind speeds all that much? There's a lot of challenges here associated with this. Real surfaces in the real world are not particularly ideal. Real wind profiles probably don't look that much like the log wind profile, particularly if there are changes in the surface near your tower or your turbine or whatever. Alright, that's a somewhat scary topic there. Let's answer a couple quick questions before we finally wrap this lecture up. Question 6. The value of h is the blank at a given location. The height of the top of the boundary layer, the height of the top of the internal boundary layer, the height of the top of the transition layer, or the height of, that was actually the height of the bottom of the transition layer, or D, the height of the top of the transition layer. Which of those is what h meant in those equations? Make a choice from those 4 options and get a little feedback before you move on to question 7.